So welcome to the third lecture series on model-free reinforcement learning. So in this class, we will talk about model-free prediction, and in the upcoming class, we will talk about model-free control. So, where are we right now? So in the last two videos, we got to know the general reinforcement learning setting. So we learned about the agent environment interface. We learned about action states and rewards. We also have seen that the agent interacts with the environment and does this over a sequence of discrete time steps, which could be meant through episodic or continual tasks. And we defined the policy as a stochastic rule to select actions to which our agent can behave. We also formally described MDPs, so Markov decision processes, as a tool to describe our reinforcement learning problems. And the main ingredients has been the states, the actions, the state transition probabilities, the return, and the discount. We also defined value functions in order to describe the expected return that we can expect actually following a particular policy. And we also defined in the last lecture, when we introduced dynamic programming methods, we defined Bellman equations as an expression of the relationship between the value of one state and the value of its successor states. Speaking of which, dynamic programming, we actually learned about two algorithms. The first one was value iteration, the second one was policy iteration, and we learned them as methods to find optimal controllers. So actually optimal controllers meaning that giving us actions that we can select upon seeing a state in order to maximize the expected return. And such dynamic programming methods are actually guaranteed to find optimal solutions for both Q and also V in polynomial time, depending on the number, so with respect to the number of states and actions. And they are exponentially faster than direct search. We could also, some of these algorithms or some of these equations you can also solve through analytical methods, but they are actually cubic in the number of states and actions, and dynamic programming actually caches the solutions and it gives us the perfect or the best solution in polynomial time. We also defined the generalized policy iteration framework to compute a value function under a given policy, which we can use to improve the policy while value iteration actually directly worked on the state set. Both of them do perform sweep through the state set. They both implement the Bellman equation update, and they both use bootstrapping. This was the general framework we defined, estimating a value function given a policy pi, and then greedily updating the policy and then reevaluating the value function. And the problem is, we could consider our reinforcement learning problems to be solved, but this would be very boring because that would mean that we're done so far. So you do not need to watch any further lectures or videos. We can solve any reinforcement learning problems. However, it turns out that dynamic programming methods are very limited to apply in practice. Maybe take a minute and think about why we actually do not see dynamic programming so much if we talk about reinforcement learning. So the general problem is that through the Bellman equation updates that we actually implement, we need a complete and accurate model of the environment. This does not only mean that we do need a model that actually represents our reward function well enough, but it's really about also about the probability transition matrix that actually defines the dynamics of the environment. And although we may know them, actually they need to be really accurate to actually use dynamic programming to find a solution on that. So, as we usually cannot assume that we know the general dynamics of the environment, so if you're acting, for instance, in some real grid world examples. So if you really have a robot in there, you would need to define like pressure of the environment and friction on the ground to really accurately represent the environment and the environment dynamics. And this is something that you usually do not have in practice. There's another thing. Even if the environment dynamics would be accurately known, it might also be the case that the possible moves and variance are just too much. So actually that you cannot just represent your state space in a table on your machine, which is like also a very common problem. So if you think about board games such as chess or also Go, the available number of possible states that you need to actually maintain in memory to represent your value function would just not fit into memory, which is basically also problematic in practice. And the thing is, maybe you do not need to know the value of each state, but also on the states that are actually happening in practice. This leads us to this lecture. So far we discussed methods that, or we assumed that we know our MDP model completely. So we just used dynamic programming actually to plan, and we solved the MDP. We considered it then solved. And the question is, what if you don't know the model? So if you don't know P, or if you don't know R, or if you don't know both of them. And this is actually what we want to do here. We distinguish between two problems for unknown MDPs. The first one is model-free prediction. So how can we actually evaluate the future given a policy pi? So how can we actually estimate a value function if we follow a policy pi? We call this model-free prediction. And the second one is model-free control, which actually says how can we optimize the future? So how can we actually optimize the value function or the expected return by finding the best policy pi? In other words, now also like considering the difference between what we did before in in dynamic programming, where we actually know the MDP, and now in the model-free methods, when we actually solved the game, or Grid World in the example from the beginning, we did not actually play Grid World, or we did not actually play the game. Instead, we knew how the game worked, and then we solved it analytically. And now in this lecture, we will actually play the game. This is the difference. And let's see us in the next videos.